I printed this because it's going to be kind of wordy here at the beginning. I wanted to show you some pictures and talk about a few things. So I wanted to just save you some writing there. First thing we know about point estimates, it's basically just what you're using from the statistic to talk about the parameter. And the point estimate we've been looking at is the p-hat, population proportion. If we're talking about the mean, if I want to estimate the mean of the entire population, we could do that by finding the mean of our samples. So we can look at x bar as the point estimate for the population mean, mu. So here is our first question. Pennies minted after 1982 are made from 97.5% zinc and 2.5% copper. The following data represents the weights of 17 randomly selected pennies. Treat this as a simple random sample. Estimate the population mean. So I want the mean. I want x bar. How do you get your mean? Add them up and divide by the total, which was what? How many? 17. So let's add these up. What did you guys get when you add those all up? 41 point what?
89.
And then if you divide that by 17, we get 2.4641 approximately. So we all remember how to find x bar? All right, so if I picked a different sample of 17 pennies, would I get the same mean? No. If I got the entire population, every penny minted after that time, and got the mean, would it be 2.4641? No, just like when we were talking about p-hats. Every sample, you're probably going to get a different number. So we can't say the mean of the population is this amount. We can only approximate. So that's why we have the need for a confidence sample. Because I know that every sample I pick will likely have a different mean. We need that confidence interval to give us a range of values to say the true mean is probably between these two things. So just like we were doing with p-hats. Now this one is a little bit different. We are going to look at a new distribution here. So we have been focused on the normal distribution. Chapter 7, Chapter 8, the beginning of Chapter 9, all of that was based off the normal distribution. Now we're looking at what's called the student's t distribution. In this, n is still your sample size, but if the original population is normal, so my pennies themselves, the weights are normal, then the distribution for their sample means for x bar will follow the t distribution. In this, we have to talk about degrees of freedom. Degrees of freedom is always one less than your sample size. X bar is your sample mean. You have your mu is the mean of the entire population. S is the sample standard deviation. So all of these variables we've seen before. Some of them have been a little bit. But we are going to be finding t this time. So this example I've done for you on the next few slides. So we got we had 1,000 different samples of size 5 from a population with a mean of 50 and standard deviation of 10. So I had 1,000 different groups of 5. We could find the sample mean and sample standard deviation. So you can find your z's, you can find your t's. If we look at the histograms for z and for t, okay, here's the z. So does that look pretty well normal? Yeah, it's basically normal. It's not perfect, but it generally follows that shape. Now when we look at the histogram for t, what we see is it looks normal on the end, but what happens on the sides? The tails go a lot further. So it's not a perfect normal distribution because those tails are so stretched out. So your z is normal and bell-shaped, centered at 0, but that's just our typical normal. But the t, it's symmetric and bell-shaped, but we have the longer tails, so it is not really normal. We have too much dispersion, too much spread. The standard deviation is too big. So that's why we have this t distribution that we're looking at, because it doesn't follow the normal pattern exactly. So your book tells you all kinds of properties for the t distribution. It is different for different degrees of freedom. If you guys look at your formula sheet, the back page, this is the table for your t distribution. So you'll notice it has the top, these are like your probabilities, but down the side it has degrees of freedom. That degree of freedom is going to be based off your sample size. So it's always one less than your sample size. So we'll have to look at our degrees of freedom. Just like the normal distribution though, it's centered at 0 and it's symmetric on both sides. The total area under the curve, it's probability, so it's 1, half on each side. The difference is the area in the tails as it spreads out is a little bit more than the normal distribution. So the normal distribution, you have more in the center and very little on the ends. Since these tails go so far, it's less in the center and more at the ends. The bigger our sample size, the more normal this appears. And we've kind of talked about that before, that in general, the higher our end, the more normal it is. So that just kind of shows you in this picture. We've got a couple different t values. This first one is the green here is with t equals 5. Then we've got this pink one with the 15 and the normal curve. So the more we have, the more normal it gets. T alpha notation, we talked about z alpha. It's been a long time ago. It's in chapter 7. It'll probably show back up when we get on that test. That alpha, z alpha, was the area to the right. We've kind of been doing that with the z alpha over 2, except I wasn't really going back and talking about it in that term, so I was just kind of reasoning through it with you and looking at it a different way. So when I give you that subscript, that's the area to the right. Here is the difference. If you look at your t distribution table, what part is shaded? Right. The area to the right. So unlike the normal table, where the numbers in the table were area to the left, this t table is giving you the area to the right. So it's always at the top, you know, if you look at that curve, but that is a difference in how these tables are read. Okay, so let's just start calculating something. So we want the t value such that the area under the t distribution to the right of the t value is 0.02, assuming 10 degrees of freedom. So another way I might write that is t with a subscript of 0.20. So we know that this area is 0.2. We need our t. So if you look at your table, unlike with the normal table, area to the right, that's what this tells me, so I don't have to do 1 minus or anything. We have 10 degrees of freedom. So you go down to, on the left, you'll go down to row 10. The top is your areas, your probabilities. So we go to 0.2, and what do we get? 0.879. everybody see that number? Why don't you guys try the next one on your own? Practice reading this table. So our area to the right is 0.1. This is kind of the opposite of how we read the normal table. You know, in the normal table, the z value is going around the outside and the probability is in the middle. On this table, the probability is across the top and the t is in the middle. So my probability is 0.1, degrees of freedom is 15, so you go down to 15 and over to 0.1, and you should get 1.341 for the t value. Everybody get that? So we are going to use these t values to find our confidence intervals. Some requirements in order to make a confidence interval. We have to have a simple random sample. We have to have sample size that's less than 5% of the whole population. That way they can be independent. And the original population has to be normal. Okay. When we do the t-distribution, that's not normal, but the original data has to be. And we know that, we've talked about in the past, if the population isn't normal, then it just has to be large enough to assume it's normal. When we were talking about x bar, how big did we say it had to be to assume it was normal?
30.
30. So our actual formula for our confidence intervals, just like everything else, this is on your formula sheet. If you look at chapter 9, the first bullet on our confidence interval is the p hat confidence interval that we've been doing. Second bullet is the x bar. So it's x bar plus or minus for the lower and the upper. The t value, the t alpha over 2, times s, the sample standard deviation, divided by the square root of it. So that is what we are going to be doing for the rest of the day, just practicing building these confidence intervals. We are going to do some by hand, and then we will talk about how we can do it with a calculator as well. So let's look at this example. So our data shows reported miles per gallon of the 2011 Ford Focus automobiles for 16 different owners. Treat this as a simple random sample. We need a 95% confidence interval for the mean miles per gallon. So we want a confidence interval for the mean. That means we're talking about the x bar. We need some information to do this. When we looked at our formula sheet, we said that, if you're looking right there, it's x bar plus or minus the t alpha over 2 times s over the square root of it. So we need x bar, we need s, we need n, we need that t alpha over 2 before we can plug in to our formula. All right, so here's what we're going to do. To make life easy, standard deviation, we've done that on our calculator many times. So I want you to enter all of this data in your calculator. So remember, we go to Stat, Edit, and we're going to enter all of this in L1. I want everybody to do this, please. Get all of our information, like our x bar and our s. Do you guys want to? Stat, calculate, and one variable statistics. Now, we may need to change something on your calculator real quick. It should say list L1. If it has anything in the frequency list box, delete that out. Just leave the frequency list blank.
It was already cleared out, John. Yep.
Okay, I think you're okay.
Is yours 86? 186. So that could be
Stat, over to calculate, one variable statistics. And then we don't want anything in our frequency list. All right, and then enter through all of that. So what is our value for x bar? 36.8. Okay, our S. 2.917 approximately, depending on how many decimals you go with. What's my N? 16. Okay, it doesn't tell us our T value. So we need to figure that out. We wanted a 95% confidence interval, okay? When we looked it up with the normal table, we talked about how that means there's 95% in the middle. So how much is on each end? 2.5%, so 0.025. Okay. When we looked it up on the normal table, we had to look up 0.975 because the normal table tells us probability to the left. But the T table tells us area to the right. So we need to look up when our T is 0.025. How many degrees of freedom do we have? 15. Degrees of freedom is n minus 1. So 16 minus 1 is 15. So you are looking up T 0.025 at 15 degrees of freedom. So what is our T value? 2.131. Did everybody find that on their table? Well, that was because we wanted a 95% confidence interval. So if I changed it to a 90% confidence interval, that would change my number. Okay. All right, we have all of our numbers now, so we can build our confidence interval. So the lower one is your x bar, 36.8, minus the T alpha over 2, which is 2.131, times my S, 2.917, divided by the square root of 16. What changes for the upper one? Yeah, same things, but just a plus in the middle. So if you just hit second enter, you can bring it back up on your calculator, change that to a plus. These, again, just like all these calculations we've talked about, rounding makes a difference depending on what you rounded your standard deviation to, can change a decimal on your confidence interval. So just please make sure that you are writing everything down so I know where your numbers come from. I don't take off for rounding differences as long as I have the numbers to look at and double check everything. All right. Now, let's check this using our calculator. So on the calculator, you already have everything entered into your L1. So we will go to Stat. We go over to Tests. Do you guys remember which one we were doing when we had P hat? A. This one, you actually are going to go down to number 8. It's called T interval. Okay, when you select that, it's going to ask you a question. The first is data or stats. We have data because we put everything in L1. sometimes I may not give you the original set of data. I might just say your mean is this, your standard deviation is this. And in that case, we'll flip over to stats, and then we can change. We can enter that stuff. But we want to set it on data because we have the original data. It asks for the list. Where did you put the data? It's in L1. Frequency, that should just be 1. Confidence level, what kind of confidence interval were we building? So that should be 0.95, and then calculate. And so it gives you your parentheses, and it is 35.246 to 38.354. So it gives us to us exactly. All right. Is that all right? If I asked you to interpret this, writing the sentence, that means we are 95% confident we're not talking about the true proportion here. We're talking about the population mean. Is between 35.246 and 38.354. Okay, so what you have to remember, if you're talking about X bars with your confidence interval, you're using the T formula. Okay, the other one when we're talking about P's, we do our regular confidence intervals like yesterday. All right. Let's look at another example. So let's make a 99% confidence interval this time. Let's do this one just straight from our calculator. So what do I need to do first? Now we can just enter our data in L1 if we're going to do everything on our calculator. Then if we just want the confidence interval from the calculator, we can just go over to stat, tests. We need number 8. Input is still data, my list is still L1, frequency should still be 1, but change your confidence level to 0.99. And so it gives me 2.4516 to 2.4767. If we were to do this by hand, I think probably the only thing that we might struggle with a little bit is finding the correct t-value. Can we just practice finding the t-value to plug the numbers in? So if I'd asked you to do this by hand, 99% confidence interval. That means 99% is in the middle. So how much is left over?
0.
Right. We have 1% to split over the two ends, so each end gets 0.005. So we're going to have a t of 0.005. How many degrees of freedom would we have? 16. There are 17 pennies here, so 17 minus 1 is 16. So you would go to your table, 16 degrees of freedom, go over to 0.005, and your t is 2.921. again, we didn't have to have that because we did confidence interval on the calculator, but I just wanted to practice finding the t-value if you were doing it by hand. Any questions on that? Real quick, I'm going to add in an example here. Let's build a 90% confidence interval. Or a sample of 20 with mean 12 and standard deviation of 0.031. So this time I didn't give you the original set of data. Again, we could do it by hand or on the calculator. If we want to do this on the calculator, we have stat tests number 8, a t-interval. Your input though, you need to switch it over to stats. So put your cursor over stats and hit enter. And then it asks you questions. X bar, that's my mean. What was my mean here? 12. So you change your X bar to a 12. Standard deviation I gave you was 0.031. My N was 20. My confidence level 90.9. And then if you hit enter, it will give you that confidence interval. So if you don't have the original data, you just have to have the mean, standard deviation, and N, and you can enter all that. Yeah, right? Are you okay with that, guys?
If line has stuff in there, is it just because of the last one?
Yep, it will automatically pull the mean and standard deviation from whatever's in your L1, so you just need to change it with this example. Okay, last thing I want to do is an example where we have to find the sample size. We did some of those yesterday. So the formula for the sample size here, you'll notice it's a little backwards. We're still talking about, everything we've been doing is t-values, except when it asks for determining the sample size, it goes back to a z here. Okay, so that is the only time in these problems that we will use the normal table. It is again on your formula sheet, the second bullet under sample size. So it's very similar to what we were doing yesterday, just a slightly different formula if we're trying to find the sample size for the population mean. So in this example, we're going back to our the miles per gallon example. How large of a sample is required to estimate the mean miles per gallon? So we're estimating the mean, so that means we use the second bullet on our sample size formula. So N is Z alpha over 2 times S divided by E squared. If you try to use the first one, you're going to have a problem because it's going to ask you for a P, and we don't have P's mentioned here because we're talking about the mean. Within 0.5 miles per gallon with 95% confidence. Okay, so we need to figure out all of our stuff. My Z alpha over 2. So you can look it up a couple different ways. We've talked about looking at the probability in the table, but I also gave you that hint yesterday. If it's one of the common ones, it's down here on the bottom. So 95% confidence, my Z alpha over 2 is? Okay. We also need an S to plug in here. What is my S? That was my standard deviation. I didn't give it to you here. I was just expecting to pull it from the previous example. So when we actually did this problem, what was our standard deviation? So I would have to give it to you in the problem or we had already done it, so we have it from there. What is my error? 0.5 miles per gallon, so just 0.5. So then we plug into our n, so we have 1.96 times the 2.917 divided by 0.5 squared. So we always have to round up, so this would be 131 required for our sample. Again, it's important that I know what you're plugging in. If you had rounded your standard deviation to 2.92, for instance, you would have came up to 132 required. So you might be off by 1 depending on how many decimals you keep, so please write your work so on a test I know how you got the answer you got, okay? Any questions?